The ground beneath Campi Flegrei is rising quickly, 20 millimeters every month. Last week, European banks released 1.4 billion euros for emergency reconstruction around Naples. The money isn't for what might happen, it's for what's already begun. On June 30th, 2025, at exactly 10 UTC, seismographs across southern Italy recorded something that made scientists pause mid-conversation. A magnitude 4.6 earthquake had just torn through Campi Flegrei, the largest in a year of increasingly violent tremors. The tremor lasted 14 seconds. In Naples, 3 million people felt their buildings sway. In Pozzuoli, where the earthquake's epicenter lay directly beneath residential neighborhoods, plaster fell from ceilings and windows cracked in geometric patterns that engineers would later recognize as structural warnings. But the earthquake wasn't the discovery, it was what the data revealed afterward. Ground monitoring stations scattered across the Phlegreian fields confirmed the caldera had risen another 35 centimeters in 2024 alone. To understand the significance, consider this. Normal geological uplift occurs in millimeters per decade. What scientists were measuring represented acceleration that defied every baseline. The numbers told a story of mounting pressure. In geological terms, 35 centimeters of annual uplift isn't gradual change. It's violent acceleration. The Phlegreian Fields, a 13-kilometer-wide depression that cradles Naples like a geological amphitheater, has now bulged upward 144 centimeters since 2005. Dr. Giuseppe De Natale from Italy's National Institute of Geophysics and Volcanology had been tracking this progression for months through satellite imagery and underground sensors. The readings showed something unprecedented. The rate of uplift was doubling every 6 months, while seismic activity shifted from random bursts to systematic patterns that suggested underground structure reorganization. The system is reorganizing itself, he noted in internal reports that would later reach emergency planners across Europe. We're not observing random geological noise, we're watching systematic preparation for major structural change. What triggered international attention wasn't just the size of recent earthquakes, 5 above magnitude 4 this year alone. It was their location and frequency. They were clustering directly beneath Pozzuoli, where 80,000 people live above what geologists now recognize as an active fault network, spanning 15 square kilometers. The June 30th event represented a new threshold. Unlike previous earthquakes that occurred at depths of 3 to 4 kilometers, this one originated barely 2.5 kilometers beneath the surface. In volcanic systems, decreasing earthquake depth often indicates rising magma or increasing hydrothermal pressure, both scenarios that demand immediate scientific attention. Within hours of the earthquake, emergency response teams deployed across affected areas. 36 families were evacuated preventively from buildings showing new structural damage. Local hospitals reported minor injuries from falling debris and panic-related incidents, but no fatalities. Yet the human response revealed something more telling than the earthquake itself. Residents of Pozzuoli, many of whom had lived through the 1980s crisis, began packing evacuation bags without official instruction. Hardware stores sold out of emergency supplies within hours. Schools canceled outdoor activities for the remainder of the week. The collective memory of previous volcanic unrest had created a population that understood geological warnings better than most emergency planners. These weren't tourists surprised by natural disaster. These were communities that had learned to read the Earth's mood through decades of coexistence with geological instability. But that was only part of the story. Campi Flegrei isn't a traditional volcano. It's a supervolcano, a collapsed caldera that spans an area larger than most cities, powered by a magma chamber so vast it defies precise measurement. What distinguishes it from mountain volcanoes like Vesuvius isn't just size, it's the mechanism of destruction. Traditional volcanoes build cone-shaped mountains and erupt through central vents. Supervolcanoes operate differently. They hollow out underground chambers, store enormous volumes of molten rock, then collapse the overlying surface into vast depressions called calderas. When they erupt, they don't just destroy everything in their immediate vicinity, they alter global climate. What's happening beneath Naples represents the early stages of this system reawakening. It's Bradyseism, the slow, relentless inflation of the Earth's crust as molten rock and superheated water push upward through fractures in ancient volcanic rock. Think of a balloon being inflated from the inside, except the balloon is solid bedrock and the pressure source is geological fury accumulated over centuries. Current monitoring reveals the mechanism in terrifying detail. A network of 12 global navigation satellite system stations positioned across the caldera provides millimeter-precise measurements of ground movement. These stations communicate with satellites every 15 seconds, creating real-time maps of surface deformation that update faster than weather forecasts. The data shows the uplift isn't uniform. It's concentrated in specific zones where underground pressure finds weakness in the overlying rock structure. The maximum uplift occurs near Pozzuoli, where ancient Roman ruins sit atop the area of greatest geological stress. Ironically, the same hydrothermal activity that made this area attractive to Roman engineers now threatens to destroy their legacy. Seismographs detect microfractures opening and closing as the crust stretches beyond its elastic limit. These aren't random cracks. They're systematic failures following fault lines established during previous volcanic episodes. Each earthquake represents another section of bedrock surrendering to mounting pressure from below. The European Space Agency's Sentinel satellites capture thermal imagery, showing underground temperatures rising faster than any computer model predicted. Heat signatures indicate hydrothermal activity, underground water systems being superheated by rising magma, creating a secondary pressure system that amplifies the surface effects. These thermal readings reveal the complexity of what's occurring beneath Naples. It's not simply magma rising toward the surface. It's an entire underground ecosystem of heated water, fractured rock, and pressurized gas responding to deep geological forces. When groundwater encounters temperatures above 200 degrees Celsius, it expands dramatically, creating additional pressure that contributes to surface uplift. Underground gas monitoring stations detect increasing concentrations of hydrogen sulfide, carbon dioxide, and other volcanic gases seeping through soil and rock fractures. These chemical signatures provide early warning of magma movement, as dissolved gases escape solution when pressure and temperature change. Historical geological surveys from the 1980s provide a comparison point that chills researchers. During the last major crisis, ground rose 1.8 meters over 2 years. Current rates suggest that benchmark could be reached within months, not years, representing an acceleration that exceeds every previous episode of volcanic unrest. The physics are unavoidable. When bedrock stretches beyond its breaking point, it doesn't bend gradually. It snaps. Geological materials exhibit brittle failure characteristics under stress. They resist deformation until reaching a threshold, then fracture suddenly and dramatically. And when bedrock snaps across a 13-kilometer area beneath 500,000 people, the consequences rewrite maps. Yet what comes next could be even worse. In 1984, Maria Antonietta still remembers the sound, not the earthquakes themselves, but the silence that followed each tremor. 40,000 people holding their breath in Pozzuoli, waiting to see if their homes would still be standing when the shaking stopped. Every morning we checked if the walls had new cracks, Maria recalls, her voice carrying the weight of memory across 4 decades. Every evening we packed bags just in case. We lived between hope and terror, never knowing if tonight would be the night we lost everything. That year, Campi Flegrei forced the largest peacetime evacuation in Italian history. The ground had risen 1.8 meters over 2 years. Ancient stone buildings that had weathered centuries cracked like eggshells. Modern concrete structures developed stress fractures that engineers recognized as signs of imminent collapse. The evacuation wasn't triggered by an eruption. It was triggered by the fear of what the Earth was building toward. Over 10,000 earthquakes in 2 years had turned daily life into a survival exercise. Each tremor brought the possibility of building collapse, gas line rupture, or water system failure. We learned to sleep lightly, remembers Giuseppe Canzanella, who operated a bakery in central Pozzuoli during the crisis. Every earthquake, even small ones, meant checking the ovens, checking the walls, checking the children. We couldn't trust the ground beneath our feet. Schools closed permanently in the most affected areas. Business owners faced impossible choices: abandon investments built over generations or risk employee safety in structurally compromised buildings. Entire neighborhoods emptied as families chose uncertainty over staying above a geological time bomb. The economic destruction preceded any physical eruption. Real estate values collapsed. Insurance companies canceled policies. Banks stopped lending for property purchases in affected areas. The psychological pressure of living above an unstable volcano proved as devastating as actual geological damage. But 1984 wasn't the first warning. Between 1969 and 1972, similar uplift had displaced thousands of residents as the ground rose 1.7 meters and triggered systematic building failures across Pozzuoli. Families were relocated to temporary housing that, in many cases, became permanent as their original homes were condemned. In the 1950s, scientists documented ground deformation that preceded decades of seismic unrest. Oral histories from elderly residents describe a pattern of geological behavior that seemed almost cyclical, periods of relative quiet followed by years of increasing earthquakes and ground movement. Each episode followed the same general pattern: gradual inflation measured in centimeters per month, accelerating earthquakes that clustered in specific areas, then either violent release through eruption or slow deflation over years as underground pressure found alternative outlets. The last actual eruption was 1538, Monte Nuovo, a cinder cone that emerged overnight from previously flat farmland and buried villages under volcanic debris. Eyewitness accounts from the period, preserved in church records and local histories, describe the earth breathing fire and ash clouds that darkened skies across the Mediterranean for weeks. Contemporary records detail the human response to that eruption: mass flight from the region, abandonment of agricultural areas, and economic disruption that affected trade routes throughout southern Italy. The new mountain, Monte Nuovo, literally New Mountain, created a permanent scar on the landscape that serves as a reminder of the supervolcano's destructive potential. What terrifies modern geologists isn't that Campi Flegrei might erupt again. Eruption is inevitable on geological timescales. What terrifies them is that current data patterns match every historical precursor to catastrophic activity, but with one critical difference: the population above the caldera has grown from thousands to over 500,000. Modern Naples represents demographic density that didn't exist during previous volcanic episodes. High-rise buildings, underground transportation networks, and industrial infrastructure create vulnerabilities that historical populations never faced. An eruption today wouldn't just displace farm families, it would require evacuating a metropolitan area larger than most European capitals. And now, scientists fear history may be repeating itself on a scale that human society has never confronted. The 1.4 billion euros announcement came with no fanfare, no press conferences, no dramatic governmental statements. On November 5, 2025, the European Investment Bank quietly approved the largest emergency geological funding in European history. The lack of publicity wasn't oversight. It was deliberate strategy to avoid panic while addressing urgent structural vulnerabilities. The money targets immediate infrastructure hardening and evacuation preparation around Naples. But reading the funding breakdown reveals the true scope of official concern. Up to 550 million euros designated for private residential buildings. Emergency retrofitting for homes that weren't built to withstand systematic seismic assault. The target includes over 15,000 structures, identified through engineering surveys as critically vulnerable to earthquake damage. Another 850 million euros targets public infrastructure, roads, hospitals, schools, and communication networks that would be critical during mass evacuation. This isn't routine maintenance funding. It's emergency preparation for scenarios that emergency planners hope never to implement but cannot afford to ignore. The road improvements focus specifically on evacuation routes leading away from the caldera. Current infrastructure couldn't handle the traffic volume that would result from rapid population displacement. The funding includes highway expansion, bridge reinforcement, and creation of alternative routes that bypass areas most likely to suffer earthquake damage. Hospital preparedness receives 200 million euros for emergency capacity expansion, trauma equipment, and communication systems designed to function during geological emergencies. These upgrades acknowledge that earthquake swarms preceding eruptions could overwhelm medical facilities before any actual volcanic activity occurs. Current monitoring data justifies the scale of financial commitment. INGV seismologists recorded 149 earthquakes in a single week, ending November 2nd. While most registered below magnitude 2, the frequency represents a 300% increase from baseline activity recorded in 2020. More significantly, the earthquakes are exhibiting temporal clustering, periods of intense activity followed by brief quiet intervals, a pattern that historical data associates with mounting underground pressure. Ground deformation measurements show the situation accelerating beyond historical precedent. GPS stations scattered across the caldera detect uplift rates that have doubled since January. Mathematical modeling suggests that if sustained, current rates would produce 1980s level ground deformation within 18 months, rather than the 2 years observed during the previous crisis. The human impact is already visible across affected areas. Building inspectors in Pozzuoli report structural damage in 60% of older constructions, ranging from cosmetic cracks to serious foundation problems that require immediate attention. Emergency shelters remain on permanent standby, staffed and supplied for rapid activation. Local hospitals have expanded trauma capacity and implemented earthquake response protocols that assume medical emergencies could occur during periods when emergency vehicles face difficult access due to damaged roads. Ambulance services now maintain equipment caches at multiple locations to ensure emergency response capability survives infrastructure damage. Yet the most telling indicator isn't scientific data or official preparation. It's economic behavior that reflects informed assessment of geological risk. Insurance companies have quietly stopped writing new policies for properties within the red zone, the area designated as highest risk for pyroclastic flows during potential eruption. Real estate values in affected areas have dropped 40% since 2024, not due to immediate damage, but due to informed recognition of long-term risk. Property sales in Pozzuoli have declined 70% as potential buyers recognize the geological uncertainty surrounding any investment in the area. Banking institutions have implemented new lending criteria that effectively prevent mortgage approval for purchases within defined geological risk zones. This isn't official policy, it's actuarial assessment translating geological data into financial reality. On November 6th, Italian Civil Protection conducted Campi Flegrei 2025, a massive evacuation drill testing scenarios for moving 500,000 people away from the caldera within 72 hours. The exercise revealed logistical gaps that emergency planners are now racing to address: insufficient temporary housing, communication bottlenecks during mass population movement, and transportation capacity limitations during peak evacuation demand. The drill also tested public response to evacuation orders. Results showed that 80% of participants understood and followed evacuation procedures, but 20%, representing potentially 100,000 people, either failed to receive emergency communications or chose to ignore official instructions. These findings drive current efforts to improve emergency communication systems and public education programs. Because what happens next could rewrite maps across southern Italy and beyond. The monitoring data contains a contradiction that keeps geologists awake at night, checking seismographs at 3 a.m. and refreshing satellite imagery feeds like worried parents watching a sick child. While surface indicators show accelerating unrest that exceeds every historical precedent, deep magma chamber readings remain frustratingly ambiguous. Some thermal signatures suggest increasing volcanic pressure at depths where magma chambers typically store molten rock. Temperature measurements from deep boreholes show heating patterns that could indicate fresh magma injection from deeper sources. Gas chemistry samples reveal increasing concentrations of magmatic gases that typically precede eruptions. But other indicators suggest the movement could be purely hydrothermal, underground water systems responding to geological stress without direct magma involvement. Pressure readings from geothermal monitoring wells show patterns consistent with heated groundwater circulation, rather than rising molten rock. Seismic wave analysis reveals fracturing patterns that could indicate water movement rather than magma intrusion. Dr. Francesca Bianco from INGV summarizes the uncertainty with characteristic scientific precision. We can measure what the Earth is doing with extraordinary accuracy. We cannot yet predict what it will do next, because we're observing a system that operates according to physical laws we understand in principle, but cannot forecast in practice. The challenge represents a fundamental limitation in volcanic science. Current monitoring technology can detect changes in real time with precision, measured in millimeters and fractions of degrees. But prediction requires understanding causal relationships between observable phenomena and future geological behavior. Relationships that remain partially hidden beneath kilometers of solid rock. Current models suggest three possible outcomes, each supported by different interpretations of the same data. The first scenario involves continued slow deformation over years, similar to recent patterns but without catastrophic release. This outcome would require underground pressure to find gradual release through existing fractures and gas emissions, essentially allowing the system to vent stress without major eruption. The second possibility involves rapid deflation, as underground pressure finds alternative release points through lateral intrusion or deep circulation changes. Historical precedent exists for this scenario. Previous episodes of bradyseism that ended through gradual pressure release rather than eruption. This outcome would bring relief to local populations, but would require ongoing monitoring to detect future pressure accumulation. The third scenario represents escalation to volcanic eruption, the outcome that would justify every euro of emergency preparation and every hour of evacuation planning. Eruption probability assessments vary widely among experts, ranging from 10% to 40% within the next decade, reflecting honest acknowledgement of predictive limitations rather than scientific consensus. Each scenario carries different implications for the 500,000 people living within the caldera's influence. Continued slow deformation would require ongoing adaptation to seismic activity and gradual infrastructure damage. Rapid deflation would bring psychological relief but potential economic consequences from emergency investments that proved unnecessary. Eruption would trigger the largest emergency response in Italian history. What scientists agree on is trajectory rather than timing. The system is moving towards some form of resolution, either through gradual pressure release or sudden geological reorganization. Current monitoring can detect changes in real time but cannot predict when the system will reach whatever threshold determines its future behavior. Dr. Christopher Kilburn from University College London, who has studied Campi Flegrei for 30 years, offers perspective that frames the uncertainty. We're watching a system that operates on timescales much longer than human planning cycles. It can remain dormant for centuries, then transform into active volcanism within months. Our challenge isn't scientific ignorance, it's geological complexity that exceeds human prediction capabilities. Meanwhile, 500,000 people continue daily life above an active supervolcano. Schools operate with earthquake drills, businesses plan futures while maintaining evacuation protocols. Families raise children in a landscape that geological time considers unstable, but human time must treat as home. The contradiction defines modern life in the shadow of Campi Flegrei. Geological reality operates according to timescales measured in centuries and millennia, while human society requires planning measured in months and years. Emergency preparation assumes the worst-case scenario could occur tomorrow, while daily life assumes it won't occur for generations. Recent developments suggest the luxury of long-term uncertainty may be ending. Accelerating seismic activity, increasing ground deformation, and mounting pressure signatures indicate the system is approaching some form of resolution. Whether that resolution involves continued unrest, gradual stabilization, or catastrophic eruption remains the question that drives emergency planning and haunts scientific analysis. The question isn't whether Campi Flegrei will reach a breaking point. The question is whether human society can adapt faster than geological forces can escalate, and whether 500,000 people can coexist indefinitely with uncertainty that grows more pressing each month. Stay curious, stay informed, and keep watching the earth beneath your feet.